Hi, in this video, we are going to start looking at part 2 of our functional equations section. So we have already had one video on this section for the course, and we are looking at this second video. We'll be talking about a couple of ideas here. This problem is a standard problem, and after that, we'll look at two new methods that you should learn and you should be exposed to, basically. So let's get into it. So the first question says that find all real numbers a for which there exists a function from R to R such that for all xy belonging to real, we have f of x plus f of y by 2 is greater than equal to f of x plus y by 2 plus a mod x minus y, right? So we have to find all the real numbers a for which this relation is true, or at least there is a function which satisfies this relation, right? So let's look at the case where a is less than equal to 0 here. If a is less than equal to 0, basically this quantity will become negative, right? So we can say that if we are able to prove or find a function such that f of x plus f of y by 2 is greater than equal to f of x plus y by 2, if this result is true for some function, then obviously f of x plus f of y by 2 will be greater than equal to f of x plus y by 2 plus a mod x minus y. Why is that? Because if this first inequality is true and a is negative, then this quantity is negative and it makes the right hand side even smaller. So the second inequality has to be true, right? So our job is to just discover a function for which this first inequality is true, and then for the case that a is less than equal to 0, we are done. We have shown that there exists a function like that, right? So let's guess some functions here. If you think of f of x is equal to x square, if this is my guess, then let's see what happens. F of x plus f of y by 2 is x square plus y square by 2 is greater than equal to x plus y by 2 whole square. This is the relation. This is the first inequality for the guess function, which is x square. And this is actually true because you will get x square plus y square plus 2xy by 4 here. And here you have x square plus y square by 2. And if you simplify this a little bit, you will end up getting 2 times x square plus y square is greater than x square plus y square plus 2xy. And this is obviously true because if you take everything on the left hand side, what you end up getting is x square plus y square minus 2xy is greater than equal to 0, which is x minus y whole square, right? So what we have seen here is that for f of x is equal to x square, the first inequality is true, right? And if the first inequality is true and a is less than 0, then the second part of it is negative. Therefore, the overall inequality is definitely true. So now we have said that for a is less than equal to 0, there exists a function, right? There exists a function f of x is equal to x square, such that this relation is satisfied. Okay, so one particular possible set of a's we have already found, which is a less than equal to 0. We also should check the case when a is greater than 0, right? So we'll do that on the next screen. So if a is greater than 0, we will now show that there is no such f of x. Show that there is no f of x such that f of x plus f of y by 2 is greater than equal to f of x plus y by 2 plus a times mod x minus y. So we'll be able to show that for positive a, there is no function like this, right? So how do we show that? We'll assume by contradiction. Let's assume if such a function f of x exists for some a greater than 0, then for all n and I belong to natural numbers, let's use this inequality, right? Let's put x to be equal to I plus 2 by n and y to be equal to I by n, right? So what are we doing here? We need to show that this result is true for all xy belongs to real, right? So this result is supposed to be true for all xy belongs to real. We have taken the case a greater than 0 and we are assuming that such a function exists for some a, right? Then what we are saying is let's put x as I plus 2 by n, where I is a natural number, n is a natural number. And let's put y as I by n, right? If I do that, let's see what the inequality looks like. So we have half of f of I plus 2 by n plus f of I by n is greater than equal to f of I plus 2 plus I by 2, right? So it is 2i plus 2 by n into 2, which is I plus 1 by n. Basically, I plus 1 by n is x plus y by 2, right? Plus a times x minus y modulus is going to be 2 by n, right? So this result is true in this case. If you put x as I plus 2 by n and y as I by n, you are getting this result. Let's simplify this result a little bit by multiplying 2 here. You get f of I plus 2 by n plus f of I by n is greater than equal to twice of f of I plus 1 by n plus 4a by n, right? Okay. So we are getting plus 4a by n, and now we will rewrite this equation in this way. So we'll say f of I plus 2 by n minus f of I plus 1 by n. We have taken one term from here to the left hand side is greater than f of I plus 1 by n minus f of I by n plus 4a by n. Let's call this as a new relation in this case. Let's call this 2, right? Now, what I want to do is I want to use this to come up with some conclusion about f of x. So if you think about it, this is like a relation where I can take any values because you had x and y were supposed to be real and we have taken I as a natural number, so I can be 0, 1, 2, whatever, right? So we will be using this inequality to come up with some claims about the function, right? So let's do that on the next screen. So I'll just go there. F of, we have I plus 2 by n minus f of I plus 1 by n is greater than equal to f of I plus 1 by n minus f of I by n plus 4a by n. So this is our second result. And if you see the structure of this inequality, you will realize that there is some telescoping series possibilities there here, right? If you take I as different values, for example, I is equal to 0, 1, 2 till n minus 1, right? If you take I as 0, 1, 2 till n minus 1, what should you get? Let's write it on the side here. If you put I as 0, what happens? It becomes 2 by n minus f of 1 by n is greater than equal to f of 1 by n minus f of 0 plus 4a by n. And then if I put I as 1, what I will get is 3 by n minus f of 2 by n is greater than f of 2 by n minus f of I as 1. So 1 by n plus 4a by n, right? So if I add up all of these cases, here I was 0, here I was 1. If I was n minus 1, what will we get? If I was n minus 1, we should have f of n plus 1 by n minus f of n by n is greater than equal to f of n minus 1 plus n by n minus f of n minus 1 by n plus 4a by n, right? So you can see clearly that there is telescoping series type of situation happening here. F of 1 by n and f of 1 by n gets cancelled. So if you add up all of these results, you will end up with the first term of the last inequality and the second term of the first inequality, right? So you end up getting here, if you simplify this after adding, you end up getting this result. F of n plus 1 by n minus f of 1 by n is greater than or equal to f of, notice here, the last term here is n by n. So that is f of 1, right? And the first term here is f of 0. So f of 0. And how many inequalities are there? There are 0 to n minus 1. There are n inequalities. So 4a by n keeps getting added, and n times it becomes plus 4a. Right? I hope everybody is understanding this. We are just taking I as 0, 1, 2 till n minus 1 and summing it up, right? So let's call this result as a third result, right? Now, what I will do here is I will repeat the same process again, but this time I will vary my I from 1, 2 till n, right? So if I vary my I from 1, 2 till n, I will basically delete this first term here, right? And I will add an nth term at the end when I is equal to n. So I'll write it on top instead. When I is equal to n, you're getting f of n plus 2 by n minus f of n plus 1 by n is greater than or equal to f of n plus 1 by n minus f of n by n plus 4a by n, right? Now we are adding from I1 to n, right? So you should still have the same telescoping series sort of situation, but this time the sum will be 3 by n will get cancelled, and you'll have the first term here, f of n plus 2 by n. The sum will be f of n plus 2 by n minus f of 2 by n, right? Minus f of 2 by n is greater than or equal to, on the other side, you will have the first term would be f of n plus 1 by n plus 1 by n, and the last term will be this one, which is minus f of 1 by n plus 4a. So this becomes our fourth result, right? Okay, now what I want you to think about it, I have gotten two different inequalities when I took I from 0 to n minus 1 and then from 1 to n. I want to keep doing this because I still have a telescoping nature here, right? I want to keep doing this. This time I'm going to, at the end, I'm going to take I from n minus 1 because I want n such inequalities. So here it was 0, I started from 0. Here I started I from 1. And I will keep doing this process, but now start I from n minus 1, n plus 1 till basically 2n minus 2. That will be n terms. And you do the same process, but this time you start from n minus 1, right? In that case, the sum that you will get is f of 2 minus f of 1 is greater than or equal to f of 2n minus 1 by n minus f of n minus 1 by n plus 4a. Basically, this will be your n plus 2 result, right? Because this is starting from 3. So 3, 4, you will get basically n such inequalities, right? The process is the exact same thing that we did for the first one and the second one, where we are just shifting the starting point of I and we are taking n terms and adding up the second inequality, right? We are always working with the second inequality and we are just shifting the starting points of I, right? So if I end up getting this, now you can realize that if I add this, what I will try to do now is add up all of these n inequalities, right? So if I add up all of these n inequalities, you will realize that there are many terms on the LHS and the RHS which will keep getting cancelled. Why? Because can you see that there is f of n plus 1 by n here, there is f of n plus 1 by n here, there is f of 1 by n here, there is f of 1 by n here, right? So you will realize that there are a lot of cancellations, and I will just write it briefly. So this is f of n plus 1 by n plus f of n plus 2 by n. I'm adding all these inequalities. I will add up till f of n plus n by n, which is f of 2. This is f of 2, n plus n by n, minus we have f of 1 by n minus f of 2 by n, and go on till minus f of n by n, which is f of 1 here, is greater than or equal to. I will get on the other side f of 1, which is f of n by n, plus f of n plus 1 by n. So I'm adding these terms now vertically, right? Till I will get f of 2n minus 1 by n, and then minus f of 0, 0 by n, minus f of 1 by n, minus till f of n minus 1 by n. And when I add all of these 4a terms, I get plus 4na, right? Now, what I want you to think here is which terms get cancelled. This term gets cancelled. F of n plus 2 by n will obviously get cancelled, the next term here, right? What will be left basically is this will be left because I will cancel the f of 2n minus 1 by n with this term, right? So I will end up getting f of 2 will be left there, and then f of 1 by n gets cancelled from here. F of 2 by n gets cancelled. And again, f of n by n is not cancelled. This gets cancelled, right? So if you add up properly and you see what is the sum of these inequalities, you will realize that you will end up getting this inequality. I will just write down here. You will end up getting f of 2 and this minus f of 1 will be left over is greater than equal to here f of 1 and minus f of 0 will be left over, right? Plus 4na. So this is the inequality that you will end up with after summing up all the n inequalities you got from 2. How did we get n inequalities starting from this equation 2? By putting I as 0, 1, 2 and summing up telescopically for n terms, right? So eventually after this process you end up getting this. Now think about it. Since a is positive, since a is greater than 0, this above inequality, this inequality cannot hold, can't hold for n tending to large numbers, for n tends to infinity. Why? This inequality cannot hold for n tends to infinity because we are getting that the difference between the first two terms for f2 and f1 is so much greater than the difference between f1 and f0. It is actually tending to infinity, right? So the difference between the terms tends to infinity, but f2 and f1 were supposed to be finite real numbers. They were supposed to be functions from R to R. You cannot have one real number here is greater than equal to some real number plus infinity. That is not a possibility. Therefore, we can say that such a function f cannot exist. Such a function f cannot exist because for the case that a is greater than 0, we are ending up having a function that blows up and the values of the function, the difference between two real values of the function is tending to infinity, right? For large n. So that is not a possibility, and therefore we can say that such a function exists only if a is less than equal to 0. We have already seen that for a is less than equal to 0, the inequality was true for the simple function f of x is equal to x squared. Now we have shown that for a positive, you are ending up getting an inequality that looks like this, that does not allow the possibility of any real function, real valued function, right? So that is the conclusion here, that such a function exists only for a less than equal to 0. Okay, now we move on to the next part of the video. Here we will discuss two new methods that you might not have seen before, and we will try to see how it applies to problems. But first of all, I want to introduce a concept called iterators of functions. Iterations of functions. So basically, you might have heard of something called composite function. So f of x is like a composite function where f has been taken twice. And what this means is instead of just simply writing f of x, we are inputting f of x to an f function, right? So what I would just say is this f of x can be written symbolically like this, f of 2x. So if I have an f of x, I'm going to write it as f of 3 of x. Basically, f 3 times. You have to take input x and supply it to f function, but it's a composite function with 3 f's. And here it has 2 f's, right? So basically, if I have f of basically n times f, right? That will be written as f of n of x, right? So that is just a good symbol that helps us shorten what we need to write. So sometimes in problems in functional equations, you need to handle these iterations of functions, right? So we want to understand how to find these iterations of functions given some information about f of x, right? So we'll look at it through some problems. So the first problem that we'll look at is this. Let n belong to natural numbers. Find f of n of x if f of x is equal to ax plus b for some constant a and b. So basically, we have a linear function here, and we want to find the nth iteration of f of x, basically composite n times, right? And a and b are some constants, right? So let's look at this and try and understand how we'll go about doing it, right? So the first method that we look at is called the fixed point method. Fixed point method. So if you recall in a previous video, in a previous section of the course, we had understood what fixed points were. So a fixed point of a function is the point such that f of x is equal to x. Then that x is called the fixed point of the function, right? So if you recall that, we'll be utilizing that here. So let's try to figure out the composition here. First of all, we look at the case where a is equal to 1. If a is equal to 1, the function looks like this. F of x is x plus b, right? And if you just think about it, f of x becomes what? Becomes f of x plus b. And that becomes x plus b plus b. So that becomes x plus 2b, right? So f of 2 of x is x plus 2b. Similarly, you can show that f of 3 of x is equal to x plus 3b. And by simple induction, you can prove that f of n of x is becoming x plus nb in this case. So in case a is equal to 1, we can easily show by induction that the nth iteration of the function is equal to x plus nb, right? Now, what about the case where a is not equal to 1, right? In those cases, we will use the fixed point method, right? So I will just do that now. What is this fixed point method? So first of all, if f of x is equal to ax plus b, if a is not equal to 1 and f of x is equal to ax plus b, let's find the fixed point first. So ax plus b should be equal to x, and you'll get a minus 1x is equal to minus b. So x should be minus b by a minus 1, or x can be written as b by 1 minus a, right? So x is equal to b by 1 minus a is my fixed point, right? And now you will realize that we can write this function f of x like this. We can write it as a times x minus b by 1 minus a plus b by 1 minus a. Think about it. Just simplify it and see whether this is true or not. We can write it like this: ax minus ab by 1 minus a plus b by 1 minus a. And you will realize that ax plus b 1 minus a by 1 minus a cancels and it becomes ax plus b. So basically what I'm saying is, if you know the fixed point, then you can write the linear function in this form. F of x can be written like this: a times x minus the fixed point plus the fixed point, right? Good, great. So now what we will say is, if I want to find f of x, right? F of x, that should be equal to a times f of x minus b by 1 minus a plus b by 1 minus a, right? And then again, we will say f of x was itself a times x minus b by 1 minus a plus b by 1 minus a. But again, I have to subtract a minus b by 1 minus a plus b by 1 minus a. So these two terms get cancelled and you are ending up with a square x minus b by 1 minus a plus b by 1 minus a, right? So this is coming out to be your f of 2 of x, right? So notice that there is a nice pattern. If f of x was a times x minus fixed point plus fixed point, then f of 2 of x, the composition f of x basically, is coming out to be a square into x minus fixed point plus fixed point, right? Now you can show this by an induction argument that if you assume basically that f of n minus 1 is of this form, you will be able to prove that f of n of x becomes a power n x minus b by 1 minus a plus b by 1 minus a. Now, if you are not convinced about it, try and calculate f of 3 of x. We have already shown that f of 2 of x is equal to a square x minus b by 1 minus a plus b by 1 minus a. Try and calculate f of 3 of x and you should be able to finish this induction yourself, right? So what we have seen is if you were able to write the function f of x is equal to ax plus b, and if you find the fixed point and write it like this, right, then it becomes really easy for you to basically figure out the nth iteration of the function. And what we have derived is this formula, which we'll use later as well. So overall, in general, what I can say is f of n of x is equal to x plus nb if a was equal to 1 and is a power n x minus b by 1 minus a plus b by 1 minus a if a is not equal to 1, right? So that is my nth iteration or composition of function f taken n times for a function which is a linear function. So that ends this problem. Think about the fixed point method, how we did it. We found the fixed point and we expressed the function in a slightly different way. And then we were able to easily get the nth iteration. The next question will show us a new method to find iterations also. So question number 3 is basically find f of n of x if f of x is equal to 2x square minus 1 for mod of x less than equal to 1. So in this question, we are going to introduce the method of bridge functions. So first of all, what are bridge functions? What are bridge functions? So we are going to apply a definition here. If there exists a function phi of x such that it has an inverse phi inverse of x and f of x is equal to phi inverse of g of phi of x. If f of x can be written as phi inverse of g of phi of x, then we say that fx and gx are similar through the bridge function phi, of x. Now, there's a lot to unpack here, but just focus on it for a bit. We are just saying that if we have a function f of x and there is a new function phi of x such that phi of x is invertible and there is a third function g of x where f of x can be written as phi inverse of g of phi of x, then we will say that f and g are similar through the bridge function phi of x. Now, this condition can be rewritten in a slightly better way. You can take phi on both sides and you can say that phi of f of x is equal to g of phi of x. And this is where the definition comes along this is where you realize that f and g are similar through the bridge function phi of x. So phi of f of x is g of phi of x. If this result is true, basically you will say that f and g functions are similar through the phi function. Okay, and the phi function becomes your bridge function. Now, why are we doing all this? We will see the application soon. So first of all, let's try to use this definition to find out what is f of 2 of x, right? What is f of 2 of x? So now what we have is f of x is equal to phi inverse g of phi of x, right? Basically, f and g are similar to the phi bridge function, right? Now we need f of 2 of x, which is equal to f of x, right? So that will be equal to f of phi inverse g of phi of x, right? So this is true right now. And then we can say that actually it is better if we open the f of x in a slightly different way. So we'll open it like this. F of this, right? We can say that from here, we can say f of x will be equal to f of phi inverse g of phi of x, right? F of phi inverse g of phi of x. Okay, again, this is the same thing that I had done before. I want to do a slightly different thing. I'll just tell you what I want to do. Instead of x, I want to put f of x, right? So f of x, I want to substitute instead of x, f of x. So this becomes phi inverse g of phi of f of x. I wanted to do it inside out rather than outside in. Okay. So obviously, you know that when you do compositions, you can do it from inside or outside. I want to do it from the inside out. So instead of x in this relation, I have replaced f of x. So here instead of x, I have to replace f of x, right? So this I am writing here as phi inverse g of phi of f of x, right? Once you have this, we will write this f of x again using the original term, right? So we'll say phi inverse g of phi of f of x is basically phi inverse g of phi of x, right? So now think about it. This phi and phi inverse will go away. They will get cancelled. And you will have g of phi of x inside, right? And outside there is a phi inverse, right? So now this becomes basically phi inverse g square, right? G of 2 of phi of x. I hope you are understanding the pattern. What we are getting is f of 2 of x is becoming phi inverse g of 2 of phi of x. When f of x was phi inverse g of phi of x, f of 2 of x is becoming phi inverse g of 2 of phi of x. So there is a nice and clear pattern. And by induction, again, you can show that if f of x is equal to phi inverse g of phi of x, we can show that f of n of x will become phi inverse g of n phi of x, right? So this is the result that we have been looking for, which gives us the easy way to find the iterators or iterations of f of x or a composite f of x if we have already found the bridge function and the g function which f is similar to, right? Now we'll come back to the problem. In the problem, if you remember, we had f of x is equal to 2x square minus 1 and mod x is less than equal to 1. This was the situation, right? Now, in this case, you can say that I can take my phi of x as cos inverse of x. We will see why that is useful. If phi of x is cos inverse of x, phi inverse of x is cos x, right? And we can say that phi of f of x, phi of f of x should be equal to g of phi of x, right? So only then will we be able to find our g function, right? So phi of f of x is what? It is cos inverse of 2x square minus 1, right? Cos inverse of 2x square minus 1. And if you think of this, you will realize that this thing, if you put x as cos theta, you will get basically 2x square minus 1 is 2 cos square theta minus 1. So that will be cos 2 theta, right? 2 cos square theta minus 1 is definitely cos 2 theta. So therefore, you have 2x square minus 1 is cos 2 theta and cos inverse cos 2 theta is 2 theta, right? And 2 theta is equal to 2 cos inverse x, right? And cos inverse x was my phi of x, right? So that implies that 2 phi of x is coming here. That implies that my g function should be 2 of x, right? G of x is 2 of x. So basically, using this function f of x and using a bridge function of cos inverse x, because we can spot the identity 2 cos square theta minus 1 is cos 2 theta. Because of that, it is turning out that my bridge function is 2 of x, right? Because it satisfies this inequality, and we have found g from here. We are not randomly guessing g. We are looking at the bridge function identity and putting f of x and bridge function. The only function that we had to guess was the bridge function. If you guessed correctly, then you will be able to spot that g becomes 2 of x, right? So what we have here is f of x is 2x square minus 1, g of x is 2 of x, and phi of x is cos inverse x, right? Therefore, and then that satisfies this condition. F of x is phi inverse of g of phi of x, right? We have already verified that. Then obviously f of n of x would be phi inverse of g n phi of x, right? So that becomes what? Phi of x is basically cos inverse x. G power n would be g power n cos inverse x here, right? And outside there is a phi inverse. Phi inverse is cos x. So cos of g power n cos inverse x, right? Now remember that g of x is 2 of 2x, right? G of x is 2x. We have to find g of n of x, right? Otherwise, we cannot evaluate this. G of x is a linear function, and we have to find the nth iteration of g of x. Otherwise, we cannot find the nth iteration of f of x, right? But using the previous problem, if g of x is 2 of x, you will realize that this is a linear function of the form ax plus b, where if a was not equal to 1, f of n of x was coming out to be a power n x minus b by 1 minus a plus b by 1 minus a, right? And in this case, actually a is equal to 2 and b is equal to 0, right? If you put a is equal to 2 and b is equal to 0, you will get g of n of x is simply 2 power n x, right? You can use the previous problem's result to get g of n of x, and therefore this is basically equal to cos of 2 power n cos inverse x, right? Cos of 2 power n cos inverse x. So our f of n of x becomes this function. This is our answer for the problem. If f of x was 2x square minus 1 and mod of x was less than equal to 1, our f of n of x becomes this. Now you will realize, as an aside, you should notice that if f of x was 2x square minus 1, which was equal to cos of basically 2 cos inverse x, right? So notice that when you had a term like this was a polynomial of degree 2. Polynomial of degree 2. In case you have a function like this, f of x is equal to cos of n of cos inverse x, you will end up getting this should be equal to a polynomial of degree n. Polynomial of x of degree n. And these types of polynomials in theory are known as Chebyshev's polynomials, and they have a lot of application in higher physics and maths. So you should know that as a normal trivia fact. In this particular problem, we got that if f of x was 2x square minus 1, we got by the bridge function method that f of n of x is equal to pi inverse g of n of pi of x. And since our phi of x was equal to basically cos inverse x, pi of x was equal to cos of x, and g of x was equal to 2x. Therefore, g of n of x was equal to 2 power nx from the previous problem. So we eventually got that f of n of x became equal to cos of 2 power n cos inverse of x, which will be a polynomial of degree 2 power n, right? According to this statement. So that is an interesting problem, and this is the second method that I wanted you to know, which is the bridge function method. Lastly, we'll end with a nice problem, which is slightly different and very interesting. So we'll look at this one. Question 4. Let a function from R to R satisfy the following conditions. Following conditions. For all xy belonging to real, mod of f of x minus mod of f of y, mod of f of x minus f of y is less than equal to mod of x minus y. This type of thing has appeared in JEE as well. This type of inequalities have been seen in JEE questions as well. However, that is not the focus for us right now. Then there exists a k belonging to n such that f of k of 0 is 0. Basically, this means f of 0 is 0, where this is done k times, right? Composition k times, right? We have to show that either f of 0 is 0 or f of 0 is 0. So if there is a function which satisfies the first condition and the second condition, we have to show that either f of 0 is 0 or f of 0 is 0, right? Now, the way we will do it is we'll try to think about the k here. So we can say that there exists a k such that this is 0. So we can say that we let k be the smallest integer such that f of k of 0 is 0, right? We need to show that k is either 1 or k is equal to 2, right? We need to prove that k is 1 or k is 2 according to the conditions of the problem, right? So we will prove by contradiction. So we'll suppose k is greater than equal to 3. We are assuming k is greater than equal to 3. Therefore, that because it is the smallest integer such that this result is true, this means that f of 0 is not equal to 0 and f of 0 is also not equal to 0. Do you understand why? Because we are assuming k is the smallest integer at which the f of k of 0 is 0. So any integer less than that will not be 0. So we are supposing that k is greater than equal to 3, right? That is the contradiction argument. Let's see what happens as a result of that on the next page. So we'll say that mod of f of 0 is equal to mod of f of 0 minus 0, right? And remember the first condition. The first condition was mod of f of x minus f of y. is less than equal to mod of x minus y. So using that, we can say that this is mod of f of 0 minus 0 is greater than equal to f of 0 minus f of 0, right? How are we getting this inequality? Think about it. Once you understand this, you will be able to figure out the rest of the problem, right? We are saying that this quantity is less than this. So think of this as our x and this as our y, right? So x minus y will be greater than equal to, this is then definitely f of x and minus f of y, right? I hope you are getting the pattern. Think of this quantity as x and this as y. So f of x minus f of y. This inequality is following from the given condition, right? Okay. So I'll rub off this stuff and we will say that this is true. Therefore, we can keep adding f's, right? We can keep adding another f to it. F of 3, 0 minus f of 2, 0, right? And so on. We can keep adding f's. We are following the same principle. This will be greater than this. Why? Because we have just added an f to both sides. We know that mod of x minus y is greater than mod of f of x minus f of y, right? If you think of this as the x and this as the y, f of 0 as x and f of 0 as y, you can say that will be greater than f of 0 minus f of 0, right? So you keep adding f's to it and you'll keep getting inequalities. So you can eventually say that this is greater than equal to f of k of 0 minus f of k minus 1 of 0, right? And now according to the problem, we know that we have assumed that f of k of 0 is 0, right? So this becomes minus of f of k minus 1 of 0, right? We are getting this result, right? Great. But we can also say that f of k minus 1 of 0, this can be written as mod of f of k minus 1 is 0, because minus 1 can be taken out of the mod, right? This thing, mod of this, is equal to mod of f of k minus 1, 0 minus 0, and will be greater than equal to, take f on both sides, will be f of k of 0 minus f of 0, right? Which will be equal to 0 minus f of 0, which will be equal to mod of f of 0, right? So from the lower this inequality here, we are establishing that mod of this is greater than equal to f of 0, and we already have mod of f of 0 is greater than equal to this, right? So basically, if you have two-sided inequalities like this, a is greater than b, mod of a is greater than mod of b, and mod of b is greater than mod of a, that obviously implies mod of a is equal to mod of b, right? So therefore, we can now say that mod of f of 0 is equal to mod of f of k inverse of 0, k minus 1, 0, right? If you have that, that implies two conditions. F of k minus 1, 0 is equal to f of 0, right? But then from here you would get f of k of 0 is equal to f of 0, right? But f of k of 0 is 0 according to our assumptions. So you're getting f of 0 is 0. But this is a contradiction, because if you recall, we had assumed that k is greater than equal to 3, and that implied that f of 0 could not be 0. Go back to the video in the beginning of the problem. We had said that f of 0 and f of 0 cannot be 0, because we have assumed k is greater than equal to 3, and k was the smallest number for which f of k of 0 is 0, right? So this is a contradiction. So this case is gone. So we are getting now the other case, f of k minus 1, 0 should be equal to minus of f of 0, right? This is the only other option that we have, right? Because the other option has been contradicted. Now let's think of this inequality and we will try to figure out what happens now. we are working under this case now. Okay. Now let's look at mod of f of 0 again. Mod of f of 0 is equal to mod of f of 0 plus 0, right? Which is equal to mod of f of 0 minus, oh no, this is not equal to that. We can write that this is f of 0 can be written as minus of f of k minus 1 of 0, and 0 can be written as plus mod of f of k of 0. According to the assumptions, we had said f of k of 0 is 0, and f of 0 we are using this result here. F of 0 is negative of this, right? So this becomes mod of f of k of 0 minus f of k minus 1 of 0, right? Now we can say that this will obviously be less than equal to mod of f of k minus 1 of 0 minus f of k minus 2 of 0, right? Because we have the inequality mod of f of x minus f of y is less than equal to mod of x minus y. So if you remove f from both terms, you will get a less than equal to inequality, right? So here there were k f's, here there were k minus 1 f's, and I've removed one f from both. So I'll get this, and there will be a less than equal to sign here. And you keep doing this process till you end up with f of 2 of 0 minus f of 0, right? Correct. Now f of, and at one more time, if you do it, you will get f of 0 minus 0 less than equal to. Great. So that implies that we are getting mod of f of 0 is less than equal to, finally you're getting mod of f of 0, right? You started out from here, you are writing it like this, and getting so many inequalities, right? And ultimately you're getting f of 0 only here at the end, right? That means since the first and the last are equal, that means all the steps before here, all the steps, the inequality is actually an equality, right? I hope you're getting the argument. We are saying the first step and the last step, we are getting the same thing. That means all of these inequalities are equals, right? Which is very interesting. The series of inequalities becomes an equality, which means for j such that j is between 2 to k minus 1, we have mod of f of j of 0 minus f of j minus 1 of 0 is equal to mod of f of 0. Why am I putting a j here? I'm saying any step here, any of these where j was between 2 to k minus 1, all of it must be equal to mod of f of 0, right? Because all of these inequalities must be equalities, right? So therefore, let's rub off some space and we will write it here itself. We are getting f of j of 0 minus f of j minus 1 of 0 will be equal to plus minus f of 0, right? And j can go from 2 to k minus 1. We are getting basically f of j of 0 minus f of j minus 1 of 0 should be equal to plus minus f of 0 if you remove the mods from this step, right? Now, we can say that if you take j as 2, for example, right, you get f of 2 of 0 minus f of 0 is equal to plus minus f of 0. So obviously, because f of 0, we saw that it cannot be 0. Therefore, we have to not take the minus sign, but take the plus sign, and we will get f of 2 of 0 is equal to 2 times f of 0, right? Similarly, f of 3 of 0 minus f of 2 of 0 is equal to plus minus f of 0. So f of 3 of 0 will be f of 2 of 0 plus f of 0. So either 3 f of 0 or f of 2 of 0 minus f of 0. So f of 0, right? Similarly, you can show that f of 4 of 0 will be equal to either twice of f of 0 or 4 times f of 0. Using this condition, for different values of j, we are getting f of 2 of 0 is twice of f of 0. F of 3 of 0 is either this 3 times or 1 time f of 0. And similarly, f of 4 of 0 is either twice of f of 0 or 4 times f of 0. So basically, again, by induction, you can show that f of, I will rub off the space here. We can show that f of k minus 1 of 0 will be equal to some integer, some positive integer times f of 0, right? Some positive integer times f of 0. So that means because f of 0 is not 0, it is basically these two will have the same sign, right? Because f of 0 is non-zero, we will get that f of k minus 1 of 0 and f of 0 are having the same sign. So they are both positive or both negative, right? But that is a clear contradiction to this statement. We were working under this case, right? We were working under this case where f of k minus 1 of 0 is negative of f of 0. And now we are getting it is a n times f of 0, which is n is a positive integer. So this is contradictory. So both the cases we got contradiction. The other case was f of 0 was equal to f of k minus 1 0. That case also we got a contradiction. And now in this case also we are getting a contradiction, which means that our initial assumption is wrong. And our initial assumption was k is greater than or equal to 3. So that means that k must be less than or equal to 2, right? And if k is less than or equal to 2, then either f of 0 is 0 or f of 0 is 0. So that concludes our problem. I hope you have understood what happened here. The problem is very interesting and I loved solving it. You should go through the video once more. If you're getting stuck somewhere, you will be able to understand the logic. Also, anyway, that goes without saying that you should try the question yourself before seeing any of these solutions. For functional equations, we'll do another video which will basically recap all of the techniques that we have learned in the first two videos. And we'll be doing quite a few problems in that third one. So those problems will not be as hard as these. Some of them are quite simple, but I just want to rehash all of the concepts once more and problem solving tricks there. So let's see you there, and hopefully you're learning something from this course so far. See you next time.